So in the first part of the lecture, we had a mistake in this slide, so I thought that I would run this again. This is the atomic read and set bits in a CSR. So what's going to happen here is that if I have in the example T0 equal 42 and I have this value in the CSR0, we need to look at the bits that will be 1 in my immediate value. So the number 4 will be, the lower 4 bits will be 0, 1, 0, 0. And here I have the lower bit equal 1. So when I do an OR between those two numbers, the change here is that this 1 has to become a 5. So this is what is supposed to happen. This is the correction to this line. And then we start talking about the organization of the RISC V processor. So we have the CPU that we already know. And then we have the CPU accesses memory, and we have focused on that part of the processor up to now in 229. Today, we are introducing the control and status registers because we need them to process exceptions and interruptions. And there is another part of the processor that is the floating point unit that contains the floating point registers. That's what enables us to operate with real numbers. We are not talking about those yet, but that will be the unit that will come after we deal with exceptions and interrupts. So what are the control and status registers that are available in RISC? In RISC, you have the UE status register. So remember, there is 4096 control and status registers in RISC V, but RISC will not going to implement all of them. So you have the UE status registers. The register name number is 0, and it contains a mask that will enable enable bits. So a mask will tell you which types of instructions are enabled at any given time. Then we have the user interrupt enable that will be used to enable external interrupts, such as, for example, the timer and the keyboard interrupts. Next, we have the UTVAC, that's the base address of the trap handler, and it's stored, this base address is stored in this register. So this is the address where I'm going to go to when an exception happens, and that's the address where your exception handler will be sitting when you create an exception handler in RISC V. Then I have the U scratch register. That is a temporary register that can be used freely by the user trap handler, and we're going to see that this temporary register U scratch will be very useful for us when we implement our exception handler. And then we have the UEPC, that is the program counter of the instruction that caused the exception. So it's the address where the instruction that caused the exception was when it caused the exception. And then we have the uCause that will tell us what the exception type was, so what caused the exception. And finally, we have the UTVol, that is the memory address at which an offending memory reference occurs. So if I do a load instruction, for example, and that load instruction is to an illegal address, the value of that address will be in the UTVol. And finally, I have the user interrupt pending register, the UIP, that will tell me which interrupts are pending at any given time. So those are the ones that the interrupts that I'm not handling right now, perhaps because I'm handling an interrupt of higher priority. There are several codes that can be used to indicate the cause of exceptions. So if I have an interrupt 1, the exception code 0 will tell me that it's a user software interrupt. The exception code 1 tells me that it's a supervisor software interrupt. So a software interrupt is usually when you are asking for a service. For example, an eCall that you do in a program to ask for a printing function is a software interrupt. The exception code number 2 is reserved for future standard use, and the exception code number 3 is machine software interrupt. 4 is a user time interrupt. Remember, that will be very important for us because we're going to be using a user time in our lab. 5 is a supervisor time interrupt. 6 is reserved for future use. 7 is a machine timer interrupt. So this makes clear that RISC V is designed with the idea that there are three levels of execution. There is the execution that happens when the user program is running, and that is what you are used to because all the programs that you write are user level code. The supervisor timer interrupt are is when the machine or the RISC V is running an operating system code, for example. And the machine level is when you are running software that's below the operating system. That is, for example, the BIOS from your machine. And again, then I have user external interrupt, supervisor external interrupt, and machine external interrupt. And I have one code that's reserved. And then I have several other codes that to form the 16 possible versions that are also reserved for future use. They have not been defined yet. So what happens when an exception occurs? First, the processor will jump to the code that starts at the base address of the trap handler. And this base address is stored in the UTVEC register. So this is the first instruction of the exception handler that will be executed. And then the exception handler will first check to see what was the cause of the exception so that it knows what it has to do. Then it will jump to the operating system handler for that exception. So the operating system will have several different handlers, one for each type of exception, and you need to jump to the right address. And the operating system then will do one of those things. It may terminate the process that caused the exception. It says your program has to be killed. For example, it's a segmentation fault. There is nothing that I can do. I have to kill the program. Or it may perform some action and return. For example, the program may have asked for a software interrupt to print a value. So the operating system will print the value on behalf of the program and then return to the program. And that's why the exception handler has to know what was the instruction that was executing when the exception occurred. When you're going to write an exception handler, one of the big questions is, can the handler save registers on the stack? And this is a more complicated answer than it used to be. In MIPS, the answer was no, absolutely not. And the main reason that you could not use the stack in MIPS is because there was a possibility that the stack pointer itself is corrupted. And if the stack pointer itself is corrupted, and you start by storing your exception handler values into that stack, you don't know where the stack pointer is. In RISC V, the exception handler mechanism is much more sophisticated than MIPS, and there are several levels of exception handler. So in the user level, it is okay to use the stack to store temporary values. However, if you are to be writing a handler for example, the supervisor level stack handler, you wouldn't be able to use the stack. So what we're going to do in 229 this term, we're going to assume that the stack cannot be used when writing an exception handler. And the reason for that is because we want it for you to learn and to simulate the more general case where you have to account for the possibility that what is happening, the error that's happening in your program, is that the stack pointer itself is corrupted. So if you want to try that, one example would be write an odd number to the stack pointer and then do a load based on that address. That should be an illegal memory access. And in that case, if you go treat that exception and the stack pointer already has an illegal value, incrementing the stack pointer, decrementing the stack pointer by 4 and trying to store a value in there would still give you another illegal access. So in 229, even though the RISC V would allow you to use the stack to store values for the exception handler, if you are in user level, we will assume that we cannot do that. So here is an example where using the stack pointer when you are in an exception could go wrong. So for example, if I put the value 0 in the stack pointer and then I load from the stack pointer, this instruction will cause a segmentation fault, and then when you go to the exception handler, you will be accessing, so you'll be accessing again a value that's close to the register 0, to the address 0, and that would also be legal. Another one would be to load an odd address into the stack pointer. This will cause an unaligned access. In both cases, the stack pointer is corrupted, and you cannot use the stack pointer when you are processing your handler. The way RISC V enables you to use the stack pointer for the user level interrupts is because these exceptions would go to the operating system, so they would go to the supervisor level, and in the supervisor level, you're not going to be able to use the user stack pointer. So if we cannot use the stack pointer, how do we save registers that we need to save? So one thing that we need to consider right now is that we have been using in 229 for quite a while now, that there is a calling convention. When I write a subroutine, I need to save the S registers, but I do not need to save the T registers and the A register. We now have to, when we consider writing an exception handler, we need to change our assumptions, because I cannot modify any of the registers when I'm when I'm processing the code in the exception handler. I have to save every single register. So now I have a problem, because I don't have temporary registers in RISC V. In MIPS, I had 2 temporary registers, which enable me to do the initial work. RISC V does not have those 2 temporary registers. So one solution that I can do is to create a stack in the kernel area. And that is what I'm going to explain in the next part of this lecture.